Now coming to the extraction of aluminium. Extraction of aluminium. We can say that. Extraction of aluminium. So in the extraction of aluminium, the bauxite is the main ore, we can say that, which is Al2O3.2H2O, and cryolite is being added, fluorspar is being added, we can say that. Cryolite is Na3AlF6, fluorspar is CaF2, we are adding it. Alright, why you'll add it, we'll come to know later on. Now, next is aluminium is the most abundant, what you can say, metal in the Earth's crust. Abundant metal I am saying you, in the Earth's crust, we can say that. It does not occur in the free state because it is highly reactive in nature, we can say that. So the steps which I said you earlier also, for extracting any particular metal, what we do is that the first we go for the concentration of the ore, we can say that. First, the concentration of ore, where the removal of impurities is being done. Got it? And here we will be doing it by the Bayer's process, we can say that. By the Bayer's process, the impure bauxite, that is Al2O3.2H2O, is converted into a pure alumina, Al2O3, we can say that. Again I repeat, it is being done by the Bayer's process. In the Bayer's process, the impure bauxite is being converted into a pure alumina, Al2O3. Got it? Then after that, it is not necessary to convert further concentration, we can say that, of the ore to oxide is not required. That is roasting, calcination, what I said earlier. So that is not required here, because already aluminium oxide is there. So hence we do not need to convert into its oxide, because already it is oxide. Alright. Now next, the process is by reduction. How do we reduce it? Not by any conventional reducing agent, by reduce it by electrolysis. And finally we go for the refining, we can say that. Got it? So the reduction which is being done by electrolysis, that is called as a Hall-Herold's process, we can say that. Hall-Herold's process. Now in the Hall-Herold's process, when we extract aluminium from alumina, from Al2O3 we get Al. So aluminium which you are getting it, almost it is pure, 99.5% pure, we can say that. If you want 99.9% pure, almost 100% pure, then we have to go for the Hoops process. Hoops, we can say that. Otherwise it is almost pure in the Hall-Herold's process, no doubt about it, where we are getting the aluminium, we can say that. Now you understood the step. I told you the first is your concentration of the ore. Now for the concentration of ore, what we do is that we take a large tank, alright, and we add in the tank, suppose we are taking a tank here, and in the tank we put sodium hydroxide, NaOH, we put it in the tank. Sodium hydroxide solution, we take it, aqueous sodium hydroxide, we put it in the tank. Now we add, that is bauxite, Al2O3.2H2O into it, we add it into the tank. Alright, now when we add it into the tank, what happens? See here, Al2O3.2H2O plus NaOH, that is aqueous. When we are adding into it, what it happens? It forms, that is nothing but sodium aluminate, that is NaAlO2 plus, what is that? You will be getting nothing but water, that is NaLO2. So here 2 aluminium means 2 NaOH, 2 NaLO2. And here 2 OH and this here 2, so that means 3 water. So in this way, sodium aluminate you will be getting it. The temperature is maintained here, and the temperature is little bit higher than that of boiling point of water, 150 to 200 degrees centigrade. I am writing it below, I don't have the space, you can write it here itself. 150 to 200 centigrade temperature is being maintained here. Alright, we are heating it and we are getting, that is sodium aluminate, we can say that. Or sodium metaluminate also we can say. So what we do is that, that is we are putting this bauxite into the tank, as you can see. Now the impurities which are present in the bauxite, impurities are nothing but ferric oxide, silicon dioxide, manganese dioxide. These are the impurities. Now they are not amphoteric in nature. Here what you find is that aluminium is amphoteric, so it reacts with the base. Sodium hydroxide is the base, it reacts with the base. It is amphoteric in nature. Amphoteric means the substance which reacts with both acids as well as with bases. So aluminium is amphoteric, so it reacts with sodium hydroxide. But the impurities which are present in bauxite, that is a ferric oxide, silicon dioxide, manganese dioxide, they are not amphoteric. They are basic. So base and base, they will not react with one another. So hence it remains in the tank as an impurities. We can say that it remains inside the tank as an impurities. But aluminium reacts with sodium hydroxide to form sodium aluminate. We can say that. Clear? In this way, impurities are being separated out. So from that is bauxite, we got that is sodium aluminate. Now what you will do is that you will be heating sodium aluminate, NaAlO2, you will take it and you will be heating in water. You will be heating, I said. So the temperature is maintained around 50 to 60 degrees Celsius. Temperature is maintained, where we get alumina, that is Al2O3 plus, that is nothing, Al2O3 I am saying, that is I will be getting AlOH3. Got it? Sorry, I am very sorry. That is aluminum hydroxide, you will be getting it, plus NaOH, sodium hydroxide, you will be getting it. Got it? That is AlOH whole thrice. Now, sodium metaluminate is diluted with water and it is being heated at temperature of 50 to 60 degrees Celsius. Got it? And that is aluminum hydroxide, we are getting it as a result, and sodium hydroxide, we are getting it. So that is aluminum hydroxide. How do we collect? That is aluminum hydroxide. Now it is aluminum hydroxide is a precipitate. Got it? And sodium hydroxide is soluble in water. So we filter it, this particular one, the precipitate is your aluminum hydroxide. I said, aluminum hydroxide is a precipitate and this is soluble. So you filter it. On filtration, you will be getting the aluminum hydroxide as a precipitate. Now, in this insoluble aluminum hydroxide, what we will do is that we will be heating. Now we will be heating and we will be getting alumina. That is, we will be heating it further. That is aluminum hydroxide to a very, very high temperature. It is being heated around 1100 degrees Celsius. We will be getting alumina, Al2O3, and water is being released in the form of vapor. We can say that water vapor is being released. So 2AlOH whole thrice will give you Al2O3 plus 3H2. We can say that. So we are getting the pure alumina from here. From bauxite, we are getting the pure alumina. Alright. Now, how do we get this particular one? By fractional crystallization, we collect pure alumina. Fractional crystallization means we take a crystal of what you can say, that is alumina, we take it. Alright, we take crystal of alumina and we tie it in a thread and we put it in aluminum hydroxide. So all the water is going to evaporate out from aluminum hydroxide upon heating. So water is going to evaporate out and alumina sticks to that seed crystal. Al2O3 sticks to the seed crystal. The seed crystal is initially a smaller one, but after that it grows in size. As more and more of alumina sticks to it, it grows in size. So this is called fractional crystallization. By the way of fractional crystallization, we collect, that is alumina, we can say that. In this way, concentration is being done by Bayer's process. This is called as a Bayer's process. First the impurities are being removed, then after that we get aluminum hydroxide upon heating it, which is a precipitate. This precipitate is dried and still it is being heated further to get the pure alumina. By the way of fractional crystallization, we collect it. In this way, the pure alumina, we are getting it. Now, we can also get this particular process. We can also do it by another process. We can say that is known as Hall's process. This is Bayer's process. We can do it by Hall's process also. The difference is that instead of taking sodium hydroxide, we will be taking aqueous sodium carbonate. Aqueous sodium carbonate is also sodium hydroxide. We can say that. Aqueous sodium carbonate is also sodium hydroxide. Aqueous sodium carbonate. Because sodium carbonate is made up of weak acid, carbonic acid, and strong base sodium hydroxide. So hence it is also more basic in nature. We can say that. Clear? So let us see the reaction of the Hall's process. This is known as Hall's process. You can write it down. HALL''S. Hall's process. What we are doing here? Here also we are doing the same thing. We are removing the impurities from the bauxite. We are removing it. And what we will be getting? Same pure alumina. But the process is a little bit different. What is the difference here? Instead of taking sodium hydroxide solution, I will be taking in the tank. I will be taking in the tank sodium carbonate solution. So what will I get? Al2O3 dot 2H2O plus Na2CO3. We can say that. Na2CO3, we will be heating it, this particular one. On heating, we will be getting, that is NaAlO2 plus water plus CO2. NaAlO2 plus water plus CO2. So that is 2 NaAlO2. So it is that is Na2 is there. So 2 NaAlO2 plus CO2 and carbon dioxide we will be getting it. CO2 gas we will be getting it. Fine. So in this way you got NaAlO2. After that what you will do is that this NaAlO2 Got it? Which you are getting it. That is NaLO2 will, the whole thing will be taking it. Water and carbon dioxide I will take it. Got it? And I will be heating it further. I will be heating it further. That is, we will pass it through more of carbon dioxide into it to the solution along with some water, and we will be heating it further. On heating further, you will be getting, that is aluminium hydroxide. I will be getting ALOH whole thrice, and as sodium is there, first of all, this two reacts to form carbonic acid. Carbonic acid reacts with sodium to form sodium carbonate. We can say that. Alright. So in this way we got aluminium hydroxide. Again, it is a precipitate. You heat it further. Aluminium hydroxide, same thing. The only difference I said, we are taking sodium carbonate instead of taking aqueous sodium carbonate. Instead of taking, that is nothing but sodium hydroxide. That's the only difference. Same thing, aluminium hydroxide will be heating at a temperature around 1180 centigrade. I'll go for fractional crystallization. I'll be getting alumina and water. Got it? That is alumina and water I'll be getting it. Got it? The only thing is that again and again I repeat, instead of in Bayer's process I have taken sodium hydroxide, in the Hall's process we are taking sodium carbonate, aqueous sodium carbonate, and aqueous sodium carbonate is similar to sodium hydroxide only. Got it? In this way we got. Now we understood this particular one. So one part is over, that is we have converted bauxite to pure alumina. Now we will go for the Hall-Herold's process. Hall-Herold's process, where we will be extracting aluminium from alumina. We will be extracting aluminium from alumina. We can say that. Clear? Now here what we will be doing in the Hall-Herold's process. In the Hall-Herold's, H-A-L-L, Hall, H-E-R-A-U-L-T, that is Hall-Herold's process, or H-E-R-O-U-L-T. In certain book it is H-E-R-O-U-L-T, in certain book it is H-E-R-A-U-L-T, whatever it is. It is not making a difference. So it is Hall-Herold's process. We can say that. In this particular process, what we do is that this is your carbon lining which acts as a cathode. This is carbon lining. This is a tank I have taken, and inside it I have coated with carbon, gas carbon it is. So which acts as cathode. This one, it acts as cathode. We can say that. The carbon lining which acts as cathode. Now, next is we will be putting a mixture. Mixture of what? That is alumina, Al2O3, cryolite and fluorspar in the ratio of 1:3:1. That is alumina, fused alumina, the molten alumina, 1 part, cryolite 3 part. Cryolite is Na3AlF6 and fluorspar is 1 part, CaF2, 1 part. So alumina, cryolite, fluorspar, will be adding it in the ratio of 1:3:1 in this particular tank. Why? I am telling you. First let me tell you the setup. Then after that, after putting this mixture here in the tank, we will be sprinkling some coke powder, some coke dust upon here. We will be putting some coke dust, we will be sprinkling some coke powder here. Alright, some coke dust, some coke powder, we will be sprinkling it here. Now, here we will be taking, that is anode, the different carbon rods which acts as anode, we can say that. So this is your cathode which is connected to the battery, we can say, and here we will be taking a lamp, that is a charge, let me rub it this one, the charge control lamp I have taken it. This one is a charge control lamp, and this one is further connected to, this is anode, we can say that. This is connected to anode. Clear? So in this way, what you find is that this is a setup, we have done it. Now this is the opening from where we will be taking out, that is aluminium. We will be taking it out. This is an opening. Now here we have taken a tank. Again I repeat, the tank is coated inside with carbon lining which acts as a cathode, we can say. Now these are the carbon rods, that is the anode which acts as anode, we can say. That positively charged electrode, you can see it is connected to the positive terminal of the battery, and the gas carbon lining is connected to the negative terminal of the battery. So it acts as cathode and this acts as anode, and in between we have put a charge control lamp, and this is your nothing but the that is dust of carbon, coke dust. We have taken it, we have sprinkled it upon it. Now we will come to that why we have taken all this thing. That one by one I will tell you the first of all. Now first of all I will come to the electrolyte. That is electrolyte we have taken Na3AlF6, cryolite, fused alumina and fluorspar. Alumina 1 part, cryolite 3 part and fluorspar CaF2 1 part. Why? Why only alumina? You could have taken alumina here because we are extracting aluminium. So alumina we could have taken, Al2O3 we could have taken only. Why we have taken this particular mixture? Now I will come to it. Alumina is highly stable, Al2O3 is highly stable, and as a result, stable oxide, and as a result aluminium has also got strong affinity for oxygen. So hence it is very difficult to extract aluminium from alumina because aluminium oxide is highly stable, it has got strong affinity for oxygen. It cannot be reduced by ordinary reducing agent. Alright. So hence we have to take this particular mixture. Now next is, that is what you find is that moreover alumina has got that is fused alumina, which if you take as a electrolyte, it acts as a non-electrolyte. Fused alumina, it is a non-conductor of electricity and it has got a melting point of around 2000 degrees Celsius. That is better, I should say 2050 degrees Celsius. It has got a melting point. Which one? Fused alumina. First of all, it's a non-conductor of electricity and it has got a very high melting point. Very high melting point. That is alumina, we consider that. Now under such a high temperature, large amount of electric energy will be required to keep it in the molten state, to keep it in the fused state. Got it? To extract aluminium from alumina, we consider that, to maintain the electrolyte in this particular state, as I said. Now the liberated aluminium, suppose I am giving that is very high, that is energy I am supplying and I am keeping it in the fused state and I am going for electrolysis. But again the next problem is that the aluminium which you are extracting it from alumina, it has got a melting point of around 660 degrees Celsius. We consider that. It has got a melting point of around. Now that means when you are providing such a high temperature, at a high temperature the aluminium which will be formed from alumina, it will volatilize out. It will volatilize out. How will you be collecting the gas of aluminium? Alright, and how will you carry out the electrolysis of what you can say alumina with a gas? Not possible. Did you get my point? Alumina has got a very high melting point, 2050 degrees Celsius. So you have to give this particular energy. At least you have to provide enough energy of around 2100 degrees Celsius to keep it in the molten state. Fine. Now aluminium after extraction. Alright, let us say I have extracted aluminium from alumina. Of course, alumina is a non-conductor of electricity, I said. Let us say that I have extracted alumina from, Al from alumina I have extracted. Al2O3 I have extracted. Don't get confused with alumina and aluminium. Understood what to say? The name is almost similar. So in this way, I have extracted aluminium from alumina. Let us say I have extracted. It is not possible under this condition. I am just giving an example to you. I have extracted. Now to keep what you can say this aluminium in the molten state, that is alumina in the molten state, I have to provide a 2050 degrees Celsius, very high temperature. Under this temperature, what will happen is that if aluminium is extracted also, it will vaporize out because aluminium has got a melting point of around 660 degrees Celsius. You are providing a temperature of around 2100 degree at least. So under this temperature, aluminium will vaporize out. With vapor, how will you go for electrolysis? How will you do electrolysis? Not possible. Alright, so hence this condition is not at all feasible to carry out the electrolysis. So hence we take a mixture of cryolite and fluorspar. Now cryolite and fluorspar, what they will do? They will not only lower the fusion point, the melting point, alright, of the mixture, alright, and also it will enhance the conductivity of the mixture. That means it will make it conductive. I said you already, alumina, that is Al2O3 is a poor conductor of electricity, is a non-conductor of electricity. By adding cryolite and fluorspar, it becomes conductive straight away. Alright, and also it lowers the fusion point. Alright, it brings it to around 950 degrees Celsius. We can say that the fusion point of alumina comes to this, not aluminium. Aluminium is 660, but alumina from 20450 it comes to 950 degrees Celsius. The fusion point is being lowered. We can say that. So we did not have to supply a huge amount of energy to what you can say keep alumina at a fused state. Got it? Definitely 950 degrees Celsius is less than 2050 degrees Celsius. Na? It is quite less. So definitely you have to require less amount of energy to keep the alumina in the molten state. Got it? Clear? And also by adding cryolite and fluorspar, it becomes conductive. The mixture becomes conductive. It conducts electricity. We can say that. Got it? Understood? It enhances the mobility of the free ions. It enhances, and also it brings down the fusion point. We can say that. So hence cryolite and fluorspar is being added. Understood now? Why do we add this particular mixture? Because it does that. So in this way, the difficulties which we were facing earlier. Got it? Charles Hall, name of the scientist who did this particular process, Charles Hall. He added this particular what you can say cryolite and fluorspar, and he removed the difficulties. It now the extraction of aluminium is quite easier. We can say that it is quite easier. For that reason, aluminium is also quite cheap. Earlier, the aluminium is quite costly. It was costlier like gold. We can say that. Now it has become quite cheaper. We can say that. Extraction of aluminium has got very simpler and it has become very cheaper. We can say that. Clear? Understood now that why we are taking the particular one. Now coming to the powdered coke. Why we are adding it? Why we are adding this powdered coke? The layer of powdered coke prevents the burning of the carbon electrodes. Or it prevents the burning of the carbon electrodes, because you will see that here oxygen will be liberated in the anode. So hence what you find is that it prevents and minimizes the heat loss by radiation. We can say that. Alright, first of all, it prevents the burning of this particular carbon electrodes, and also it reduces the heat loss, because carbon is that is layer of carbon. It is a poor conductor. It does not conduct the heat. So by radiation, the heat can be lost in the surroundings. So once the heat is lost, means what? Again you have to heat it to keep it at a temperature of around 950 degrees Celsius. So when you are heating it continuously, it is a wastage of energy. Got it? And also economically it is not good for us, because the cost of production increases. As the amount of energy, more and more of energy will give, so cost of production is also going to increase. That also we have to look at. The cost of production also will come down. It should be economical also. Understood? So in this way, we are providing this particular one to prevent the heat loss, and also it prevents the burning out of this particular anode. We can say that the graphite anode which you have taken, the carbon anodes which you have taken it. Now, carbon anodes or the graphite anodes has to be replaced from time to time. And why you have taken carbon and graphite? Because it is inert in nature. It is inert. It does not react with the electrolyte. For that reason, we have preferred. Now, time to time, you have to replace the anode. Why you have to replace the anode? Because, as I said you, that in the anode, you will see oxygen is produced. This oxygen reacts with the carbon to form carbon monoxide or carbon dioxide. So, that means the graphite is being used up. The carbon rod is used up. And when it is used up, initially you are taking a thick one. Got it? Initially, it is broader electrode you are preferring it. But time to time, you have to change it. Why? Because upon using it becomes thinner. So when the cross-sectional area decreases, resistance increases. If resistance is going to increase, then less amount of electricity will flow through it. Again, it will be economically lost for the industries. Got it? So hence, time to time, you have to replace the anode. You have to take a broader anode and you have to keep, because carbon rod is being used up. Got it? We can say that. To prevent the burning of the carbon rod also, we have provided this coke dust. We can say that. So now the electrolytic reduction of alumina is a continuous process. Continuous process. How do we know? Because this charge control lamp, we have put it here, is not that now. When the charge, it becomes less. Got it? Charge means the cryolite, fluorspar and aluminium mixture. When it becomes less, then the bulb glows. Why it glows? Because as the resistance in the internal circuit, it is increased. So the resistance of the external circuit decreases, and hence the bulb starts glowing. Again I repeat, resistance in the internal circuit increases. How it increases? Because charge decreases, the amount of electrons which is required, that it decreases. Why? Because cryolite, fluorspar, alumina is being used up. So the charge is decreasing. So what you find is that ultimately charge control lamp, it is being said. Why? Because it will tell you that when to add the charge into this particular, what you can say, tank. When to add the charge. When the bulb will glow, we come to know that we have to add the charge to it. Once you add the charge, again the process goes on. So hence, that is electrolytic reduction of aluminium is a continuous process. It does not stop. It is a continuous process. Once the bulb is glowing means there is an indication that you have to add the charge into it. So you add the charge, again the process will continue. So for that reason, the charge control lamp is put. So why the charge control lamp is going to glow? For that reason I said that when the charge is decreasing here, the resistance is increasing here. So this is your internal circuit and this is your external circuit. So if the resistance in the internal circuit increases, the resistance in the external circuit, this is the wire, it decreases. So when the resistance will decrease in the external circuit, you know what will happen? Current will flow. You have read it? That is Ohm's law. Got it? Current is going to flow. As the current is going to flow, the bulb is going to glow. The bulb will glow. The glowing of the bulb indicates that yet we have to add the charge into it. Alright, so in this way, that is the charge is being added into the electrolytic tank. Alright, and the process is being continued in this particular manner. So hence, electrolytic reduction of aluminium is a continuous process. Alright, okay, have you understood what I said? Now you will see in the next one how the process carried out. Thank you.